evaluate the double integral 3x plus 4y squared, where R is the region in the upper half plane bounded by the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. So here, as usual, we'll start by sketching our domain of integration. So R is our domain or the region. So let's look at the two circles in the half plane, which really means that it's above y equals to 0 or above the x-axis, and it's x squared plus y squared equals to 1 means it has a radius of 1 units, because x squared plus y squared equal to 1 squared. This means it's a circle of only 1 units radius, and we won't have this part below because it's in the upper half plane. And the next one will have x squared plus y squared equals to 2 squared, which means it has a radius of 2. This is my region. Now, this sort of problems can be solved by using Cartesian coordinates, like in the xyz coordinates, but they are difficult to handle because in circular symmetries it's much easier to simply use polar coordinates. And polar coordinates are defined as x equals to r cos theta, y equals to r sin theta, and r equals to the positive square root of x squared plus y squared. That means r is either greater than or equal to 0. R is non-negative. R equal to 0 indicates that we are at the origin. Okay, so now let's try to solve this problem. (3x plus 4y squared dA). So let's our first target is simply to write it down, 3r cos theta. I'm just substituting x and y. 4r squared sine squared theta from here, and then with the area element in polar coordinates is dA equals to r dr d theta. So we'll put that. We've got r dr d theta. Great. So now we also need the limits. So we'll write the r limits over here. So the lower r limits will be what is the lowest value for all of these points. Since this have a circular symmetry, and we can all see that the lowest r value will be at 1. That is on this circle. If the point is above this circle, then it will have an r value which is greater than 1, because distance from the origin, which is what r really is, will be larger than 1, as the radius of the circle is 1. That means any point in over here has an r value which is larger than 1. So our lower limit must be r equals to 1, and the upper limit is r equals to 2, because if the point can be on the circle or below the circle, but it could never be over here. If the distance from the origin is greater than 2, that means it lies outside of the circle, which has a radius of 2, and hence our upper limit will be r equals to 2. And how much angle are we going? So the angle from here to here, let's say we are moving our a ray starting from the origin, and which will move anti-clockwise and fill up our entire region. So it's starting from x-axis, we will have an angle of 0. So, and as we move on, our angle will keep on increasing. In the first quadrant, we'll have an angle of pi by 2, or you might also call it 90 degrees, but we'll always use radians in calculus. So this is pi by 2. But this is not all of a region. We all have more and another pi by 2 or 90 degrees. So 2 90 degrees we have pi by 2 plus pi by 2 is just pi, right? A straight line, 180 degrees. So you have to cover theta equals to pi. This will give us this setup for our integral. 0, pi, 1, 2. Okay, we just write it down. 3r cos theta plus 4 r squared sine squared theta. Now let's multiply it out. So we have to do the r integral first. So it's 3r squared cos theta plus 4r cubed sine squared theta dr d theta. Now let's do the r integral while treating theta as a constant. So this will have r cubed and divide by 3 by 3 is just 1. So we've got r cubed cos theta plus 4 by 4 is just also 1. So we've got r to the power 4 sine squared theta. And we have to take the limits. R goes from 1 to 2 d theta. So just substitute 2. We have 2 cubed is 8. 2 to the power 4 is 16. So we have plus 16 sine squared theta. Now to subtract it with minus 1 cubed is just 1. So we have cos theta. Again 1 to the power 4 is 1. So we've got plus sine squared theta times d theta. Let's simplify this out a little bit. We've got 7 cos theta d theta. So plus this is just minus. So you get 16 minus 1 is 15 sine squared theta. So this is, we have to substitute sine squared theta with 1 minus cos 2 theta divided by 2, which we do for evaluating the integral of sine squared theta. So we do 1 minus cos 2 theta divided by 2 d theta. The first integral is simple. We got 7 sine theta. Next we have 15 over 2 theta, just a constant, integration of a constant. Then we have minus 15 over 4, because this is 15 over 2 divided by 2 coming from the integral of cos 2 theta. So you got 15 over 4. Then we have the cos will turn to a sine 2 theta. Now you just take the limits from 0 to pi. And when you do this, means 7 into sine pi, which is just 0, 15 over 2 pi, and sine 2s pi is also 0, so this term will vanish. And when we take the lower limit, all 3 terms will vanish, and that means our answer is really just 15 over 2 pi. Find the volume of the solid bounded by the plane z equals 0 and the paraboloid z equals 1 minus x squared minus y squared. So what is the plane z equals to 0? It's just the xy plane, right? And how do we find what happens at to the paraboloid at z equals 0? It's a very simple thing. So we just put z equals to 0 in this equation to find 1 minus x squared minus y squared equals to 0, which must mean that x squared plus y squared equals to 1 squared, or this is a circle of radius 1, and that means that the diagram should look like something like this. So we have a paraboloid over here, and the maximum point of this paraboloid is plus 1. As you can see, if we put a 0 in both x and y at the origin, you will get plus 1. And as the paraboloid goes down, it's in the xy plane we get this circle. Let's use a different color. Sorry. So we get this circle at z equals to 0 or at the xy plane, and this circle has this equation x squared plus y squared equal to 1. And this is just this, what we need to do in order to do the integration. We're really only concerned with the region of integration, which is on the xy plane. So it's actually a 2D diagram. We have a circle, full circle, and this is our domain D. Now we want to do the integration so that we get the volume underneath the paraboloid and onto this circular disk. So in order to do that, all we need to do is to set up the integral. So screen, volume over the region D of the paraboloid. We have the paraboloid has the equation z equals to 1 minus x squared minus y squared times dA. Now again, since we have a circular domain, we can use polar coordinates to help us, because then our integration will be a lot simpler. So let's do that. Now our circle has a radius of 1 unit here, because of this, the equation of the circle. So every point on this domain has the smallest must have an r value of greater than or equal to 0. The r equal to 0 is the origin, and anything that is not the origin and inside this disk must have some distance r, which is greater than 0, but it cannot exceed this circle, which means that the points cannot have an r value of greater than 1, which indicates that, because if it had, then the point would have a distance from the origin which is greater than 1, and it definitely lies outside our circle with radius 1. And hence all we need to do is write down the limits now. So we start from 0, indicating that origin, and as we move on, to cover all the points, the maximum r value we can have is 1. Now we have to circulate starting from theta equals to 0, and we go all the way. So we end at twice pi, 0 to twice pi, 1 minus x squared plus y squared times the dA is r dr d theta, and what is x squared plus y squared is just r squared, because r is square root of x squared plus y squared. This means that if I do the square root will go away. And now we'll just do the r integration. So here we will have, now before we do the r integration, let's just multiply it out. So we've got r minus, this is r squared, right? So we've got r cubed dr d theta. So this will be 0 to twice pi. We've got half r squared minus 1/4 of r to the power 4, and we put in the limits d theta. Now we have put 1, we'll get half minus 1/4 d theta. So this is just this this is actually 1/4, and we have theta, because we integrate with respect to theta, twice pi 0, and this will give us 1/4 2 theta twice pi minus 0. This is just half pi or pi by 2. Use the double integral to find the area enclosed by one loop of the four-leaved rows r equals to cos 2 theta. So we'll start by sketching how the four-leaved rows looks like. So sketch of r equals to cos 2 theta. Now here what we're interested is to find the area under one loop. So when does this loop reach the origin? and to find that, all we need to do is solve for the 0 of r. When is r equals to cos 2 theta, which has to be 0 at for what values of theta. So it's easy. So twice theta equals to, yeah, it's plus minus pi by 2, because cos theta is 0 for like cos pi by 2 is 0. Also cos minus pi by 2 is also 0. Both of them are equal to 0. So that means there are other values of theta as well, for which we will get 0 r equals to 0. For instance, there's going to be another angle, this angle, which will give us 0, or this angle which will give us 0, but we're not really interested in them. We just want one leaf and this one. So as we solve this, we will get theta equals to plus minus pi over 4, which is precisely these two angles, and at these two angles we can see from this graph even that we're the origin, or we're at 0. So this gives us the limits by which our angle varies. Like this leaf is, all the points in this leaf have corresponding theta values which must be greater than or equal to minus pi by 4, or basically it starts from here, and to cover the entire region we need to keep on increasing it until we hit again at theta equals to pi by 4. So this is our angular coverage. Next we have the radial coverage. So we find out the r limits. So we know that the origin is here in our leaf. That means the smallest value r can get is definitely greater than or equal to 0, because these points have r values greater than 0, as this is something positive, this is something positive. But what is the maximum bound for r values? As you can see, we cannot go beyond this particular curve. This means our r has an upper bound, which is just this leaf, this function which describes this leaf, and we know that this is just this bound must then be r equals to cos 2 theta. So then we write this down, cos 2 theta. So this means r is bounded within 0 to cos 2 theta. All the points in this region will always satisfy this relationship, also the angular relationship, and this gives us our limit. The r limits start from 0 and is bounded by this curve, right? So this curve is just cos 2 theta, and our angles vary from here to here. So minus pi by 4 to plus pi by 4, and the function that will integrate is 1, because if we want to get the area using double integral, we always have to integrate the constant function 1. In other words, area equals to the double integral over a particular region of the function 1 dA. So dA is just r dr d theta, and we integrate the constant function 1, and this is my area. So let's do this. It's actually very simple. Pi over 4 minus pi over 4 to plus pi over 4, and if I do this integration, I'll get 1 into r is just r, so you get r squared by 2. We now have to put in our limits. This is the r limit, right? So we have pi by 4, so half cos squared 2 theta minus half into 0 squared, which is 0, so times d theta. Now what is cos square 2 theta? Is just half into 1 plus cos 2 theta. Sorry, cos 4 theta. Because we have 2, so the double angle formula gives this relationship. Times d theta. We can take both the halves outside, so we get 1/4 minus pi over 4, simply 1 plus cos 4 theta times d theta. Now we got 1/4, and so the integration of 1 is just theta, and for cos 4 theta we have plus 1/4 sin 4 theta. The lower limit is minus pi by 4, the upper limit is pi by 4. Then we have, once we substitute this in, it's pi by 4, pi by 4 plus 1/4 sine 4 into pi by 4. And then we have to subtract minus pi by 4 and plus 1/4 sine minus pi by 4 times 4. And this is equal to 0 because the 4's cancel and sine pi is 0, and these two 4's also cancel. Sine minus pi is also 0. This leaves us with just minus is plus pi by 4, plus pi by 4 is just pi by 2, and pi by 2 times 1/4 is pi by 8, which is our answer. Find the volume of the solid that lies under the paraboloid z equals x square plus y square above the xy plane and inside the cylinder x square plus y squared equals to twice x. Okay, so we don't really need to draw a 3D sketch to solve this problem, but I'm doing it for a demonstration here. So we have this is the paraboloid, and this is z equals x squared plus y squared. This over here is our cylinder, which is x squared plus y squared equals to twice x. The question is asking us to find the volume that is underneath this paraboloid, like this is the surface of the paraboloid, right? Now, what is under this red surface of the paraboloid? The volume onto this cylindrical, onto this, the base of the cylinder. So the base of the cylinder is actually a circle, right? So all we really need is to integrate our paraboloid onto this circle. And to find this circle, what we need to do is we just use the cylinder's equation. The interesting thing about a cylinder is that it will depend only on two coordinates in 3 dimensions, and if you force it to be on a plane, then it's the same thing as the equation of a circle. And here we want the equation of this cylinder on the plane z equals to 0, or equivalently the xy plane. Now we will complete the square. X square minus twice x plus 1 minus 1 to get so that this is still a 0, plus y squared equal to 0, and we get x minus 1 whole squared and plus y squared. But this minus 1 that's here will go to the right and give us a plus 1, which is also the same thing as 1 squared, as 1 and 1 squared are equal. This means that our circle, now we can draw a two-dimensional diagram on the xy plane, which will help us solve our problem. The center of the circle is at 1, 0, and it has the radius of 1, so it won't really go beyond this, and it won't go beyond 2 either, and it's the whole circle. So this region drawn over here is the same thing as this. We're just focusing on the xy plane now to find the limits. We don't need the 3D diagram to find the limit. So since this is also, this problem has a circular symmetry, we can use polar coordinates to make the problem a bit easier. So in order to find the limits, let's start with theta. So, and this line over here, we have minus pi by 2. This is going clockwise, so you get a negative minus pi by 2. So it's like 90 degree clockwise. And this over here will have plus pi by 2. It's like anti-clockwise 90 degree. And these are the 2 points where these are the really we need to flip just through this angles, this whole angle, starting from here and then going through to cover up all the possible theta values within the circle, so that the circle is covered essentially. So we have theta, which must be smaller than or equal to minus pi by 2, and it must be it must be larger than or equal to pi by 2, or smaller than or equal to pi by 2 plus pi by 2. So now what about the r values? The r value, we have the origin in our domain, so this means r, the smallest value r can have is 0. R cannot be negative, so r is greater than or equal to 0. Now for these points, r is definitely greater than 0, as the distance from the origin and this particular points are positive. So what r cannot exceed is this particular circle, and it changes as we move across angles. For different lines, we see different bounds for r. This means that r is bounded from 0 till this function. So this function is nothing but our circle, and this circle can be described very easily with polar coordinates. To find the function, all we have to do is substitute our r values, x and y, into this equation. So we've got r cos theta minus 1 plus r square sine square theta, there will be a square here, equals to 1. This means that r square sine square cos square theta minus 2r cos theta plus 1 plus r square sine square theta equals to 1. Now we can take r square common, cos square theta plus sine square theta minus 2r cos theta plus 1 equals to 1. Right? So these two actually cancels, so we have, this is just 1, sine square theta plus cos square theta is 1, so we got r square minus 2r cos theta equal to 0. This means that r is r minus 2 cos theta. Now we have two solutions, where r equal to 0, which describes the origin, and the other one is r equals to 2 cos theta. R equals 2 cos theta describes all the points in this circle, including the origin, which is also described by r equals to 0. So in a way, we don't really need to write this, as it is included in this this solution. Whenever theta equals to plus minus pi by 2, we will get cos theta equals to 0, which means that at these 2 points we get the value r equals to 0. So this is not really, it's kind of redundant, we don't need this. So this is our solution, and this we call that r equals to 2 cos theta. So we know that our bound must now be this circle, since none of the points will leave the circle, so since this is the bound, this is our upper bound, we can now write down the limits of our integral. So the question wanted the volume. The volume is just the definite integral, the double integral of z dA, and our z is x squared plus y squared from the question, and this is in polar coordinates r dr d theta. And now we can write down a region using these inequalities. Our angle varies from, theta varies from minus pi by 2 to plus pi by 2, and our the r varies from 0 to 2 cos theta, and this is just r squared. We have done this before, so it's r squared times r is r cubed dr d theta. Since we will have r to the power 4 divided by 4, we do the r integration now. So now we will have 2 to the power 4 is 16. 16 divided by 4 is 4. So we have got 4 cos to the power 4 theta d theta. Now we will exploit the property of an even function, where we can shift the integral by first and start it from 0 till one of the limits, put it 2, and we just shift the interval. That's it. And the reason we can do that is, if you remember, whenever f of x is even, we have a symmetry on the y-axis, which means we have a function like which looks exactly identical. It's like if y-axis is acting like a mirror, and whenever for any interval from minus a to plus a, where of course a like minus 4 to plus 4 or minus 5 to plus 5, we have same area in both sides, and this means that the total area is double than what is from 0 to a, which is exactly the same thing used here. Since we have both pi by 2 as limits, minus pi by 2 and plus pi by 2, we can take it to 0 to pi by 2 after putting 2 here. So now this becomes 8, and we can use that cos square theta equals to, this is just a cos square and then square again, so cos square theta equals to 1 plus cos 2 theta divided by 2. Now we take 2 square is 4, 8 by 4 is 2, let's do the square. 1 plus 2 cos 2 theta plus cos square 2 theta d theta. Now let's do the integral. So we have the integral of 1 is just theta plus the integral of cos 2 theta is sin 2 theta divided by 2, so you just get sin 2 theta. Next we have to integrate cos square theta. Let's just do this over here. Cos square 2 theta d theta equals to integral of 1 plus cos 4 theta divided by 2 d theta. So now we get theta by 2, or simply half theta plus 1/8 cos sine 4 theta. I'm gonna substitute this back. We should have a plus c, but doesn't really matter. Now we take from 0 to pi by 2. So we have 2 into pi by 2 plus sine twice 2 into pi by 2 is just sine pi is 0, and half into pi by 2 is pi by 4, plus again pi by 2 into 4 is twice pi, sine of twice pi is 0. Next we have, if we put 0, all of them will become 0, so we have minus 0, doesn't really matter. So now we have 3/4 of pi into 2. This is nothing but 3 pi over 2. This is our answer.